Section 6, we're going to get into a handful of properties of solutions. There are others, and I'll mention some of them at the end. But the ones that come up here in the notes are the only ones that you need to know. So first, we're going to kind of go through properties of solutions, but also some other things that look like solutions, but technically are not. So solutions are transparent. That does not mean clear. That means see-through. And so, I don't know, Mountain Dew is transparent. The blue and orange solutions that you've seen in earlier slides. The orange one was probably potassium dichromate. It could have been some other dichromate. The blue one was copper sulfate. They're see-through, but they are colored. They do not separate. That is, they are a homogeneous mixture. And they contain small pieces. That could be particles, ions, or molecules that cannot be filtered. That is, they don't separate out of solution through normal separatory techniques. And they can even pass through semi-permeable membranes, basically things that will allow some things to pass through. Coffee filter is a great example of kind of a semi-permeable membrane. It is something that kind of lets some things permeate it, that is, pass through it, but stops other things from passing through it. That's what filter paper does. Colloids have pieces that are slightly bigger, but those pieces cannot be filtered. However, they can be separated by semi-permeable membranes. And this is where, like I said, the coffee filter is only an okay example of it, because the coffee filter really is doing filtering, but it'll allow a solution through because there aren't particles to be filtered there. A semi-permeable membrane is some kind of barrier that will allow some pieces through, but not other pieces through, and that's what colloids do. There are all sorts of great examples of colloids. I'm actually going to take some time to go through some of these because I think they're a little bit harder to understand just on their own. But fog, cloud, hairspray, dust, smoke, pretty much anything that is shaving cream, whipped cream, soap suds, styrofoam, marshmallows. They're even kind of made by whipping them. It's just that what is trapping them is different. I remember the first example that was given to me was mayonnaise, and I hate the taste of mayonnaise. In fact, it tends to make me hurl when I have it. It is a colloid. Milk is also a colloid, interestingly. And one great thing that I've done before as a demo, I'll try to post a video of it if I can remember, is a colloid demonstration where you take a container of liquid, say water, and water will let laser light just pass right through it. And so if you shine a laser towards water, it will pass through and just go out the other side. However, you can put things in the way of the laser and make them show up. And so out here, I can sprinkle a little bit of flour or some other powder, and you can make it show up. You'll see it done in movies all the time where the criminal will blow some powder and the laser beam will show up, and then they can sneak through the security detection system. The downside is usually making the laser shows up, bends enough of the laser light away that it actually blocks the receptor, the sensor, and so then it backfires and that doesn't actually work, but it's great for movies. But you could put something there in the way, hairspray, etc., to make the laser show up here, but it won't show up as it goes through the water. But if you shine it through a colloid, or even if you do something as simple as adding a little bit of it in there, and if you add just a little bit of milk in here, it will spread out, but the milk is still a colloid. And then what happens is, because those particles are bigger, when you go to shine the laser light through it instead, well, then it's just like having the particles in the air, and it shows up and you get this beam going through. There's another great colloid demonstration that I have that changes the color of light because it starts filtering out more and more colors as the colloid is formed from a chemical reaction. Again, if I can remember to, I'll post videos for those. Then we can add on to that suspensions, and suspensions are heterogeneous. That is, they're not evenly mixed, non-uniform or unevenly mixed, or uneven mixtures. They have large particles that settle out a solution. Having said that, you can end up with things like colloids and some suspensions where things say semi-suspended because they end up resting against one another and they don't fully sink out. But these can definitely be filtered out here. And so imagine that, say, you don't like pulp in orange juice. Well, when you get that orange juice, you're supposed to shake it up to spread out that pulp in there. But if you're someone who doesn't like it, you've got two choices. One is you can let it just settle out and then pour very gently, or two, you can filter it out. Now, I don't know of anyone who filters orange juice. You should buy the kind that you like instead. But a great example of a suspension is a mud puddle. That is, it has to be stirred up, and when it's stirred up, then it'll be temporarily mixed. It will look like it's a solution maybe, or like it's maybe a colloid there, but you give it time and eventually that mud will settle down, and then you end up with clear indication that it is a suspension because the stuff didn't stay suspended. Interestingly, your blood platelets, they stay suspended because the circulation system just constantly stirs them up. But it's part of why we can separate blood into its different components, because it will separate, and we can speed that up using something called a centrifuge that spins it and relies on the centrifugal or centripetal force, depending on what level of physics you're interested in understanding, to separate out the blood platelets. If you give blood, doing blood donations, they will take whole blood, or there's some where they'll hook you up to a machine and they will harvest just the platelets. There's other ones that are just plasma donations that you can do, but those things are suspended because they're constantly re-stirred. Another great example is salad dressing, and even with salad dressing, especially if you have like an oil and vinegar one, then they will separate into layers. When you mix it, they will mix, and then you actually have both a polar and density separation there, as well as any floaty bits that you might have in there from seasonings that are in there that will settle out to the bottom. And so you get some interesting different types of our solutions in there. And this is a great summary table. I'm going to encourage you to take a moment and look at that, as well as to take a moment here and look at this here. That if we have a suspension, something that is stirred up, it'll eventually settle out, or it can be filtered out where it's left behind in a filter paper here. With the colloid, you'll notice the colloids don't settle out, and they do pass through filter paper. Now, you have one shown here that's either gotten stuck or it is just not had time to pass through yet, and it does depend a little bit on the particle size of the colloid. Colloids are the weird ones, and your solution definitely passes through filter paper. And then we have this one that's a semipermeable membrane. And this one's a little bit odd, but all the stuff started in the bag here. And the semipermeable membrane does not allow the colloid or the suspension through, but does allow the solution through. And so those are your kind of different levels of things that appear to be solutions, or things that are mixtures like solution. So this one here, a mixture that has solute particles that do not settle out. So not settle out, it can't be a suspension, but are too large to pass through a semipermeable membrane. Well, only solutions could pass through semipermeable membranes, is a B colloid. That was a simple question. Semipermeable membranes are these things, barriers that allow some things to go through and other things to not go through. Water will flow from a low concentration towards a high concentration. That is, that your solvent flows from a high concentration to a low concentration. Well, from there, what ends up happening is that the volume of stuff in the concentrate side ends up going up. You end up with a higher volume. However, the water doesn't really care which side it's on, and it passes back and forth between the two sides and ends up establishing an equilibrium. And in that equilibrium, then, you end up with a certain volume of solvent over here and a certain volume over here that has then a certain concentration there. And eventually you'll get to a situation where the concentrations on both sides are the same. One great example of this that I've done before, I've never filmed it, maybe I will for you guys here now, but the biology teacher does this as a lab, is you start out with an egg and you dissolve away the shell. You can do that with vinegar. And then once you have what is sometimes called a jelly egg, you have a fairly large cell membrane. You've got the yolk inside of there, and then you can put it into a beaker with different solutions. If it's just plain water, then water will want to go into here because water will flow from high concentration to low concentration, and it'll actually puff up that egg because the egg has stuff inside of it and has a high concentration relative to the water. If, on the other hand, you put that egg with its yolk into, say, a saltwater solution, well, now the water from the egg is going to want to leave there. And so then what ends up happening is the egg ends up shriveling, and that cell membrane is a semi-permeable membrane. And if you go on to take 111 or an organic chemistry class, you'll get into how that actually works, chemically speaking, in terms of stuff going into and out of through a cell membrane through the process of osmosis. So something that comes up with osmosis is something called osmotic pressure. And it's simply the amount of pressure that you would have to exert and we're talking something like fluid pressure, very similar to gas pressure. I mean, gas pressure is a fluid, but usually since we're talking about solutions here, it's going to be a water pressure. But the amount of pressure that you would have to push against to stop the osmosis process. The more particles that you have dissolved in solution, the greater the osmotic pressure is, because water wants to go from low concentration to high concentration. And so the greater the concentration, the more the water wants to flow in. And I'm personifying the water here, of course, but the more it wants to flow in, and so the more pressure it's going to take to resist that. There is a process called reverse osmosis where we not only stop the osmosis process, but then we force it to go backwards. So osmotic pressure is how much pressure it would take to stop it. Reverse osmosis then is you have a pressure greater than the osmotic pressure. And so the pressure osmotic, and here your pressure applied, let's call it, is greater than the osmotic pressure. Then you can force it to go backwards. Well, a lot of times what we can use there is a membrane that will purify it. That is, we're moving the water from where there's stuff dissolved in it to the region where there's not stuff dissolved in it. And so it is a way of purifying the water, and it's just one way that we can do that. Reverse osmosis would be ideal for desalinating ocean water if we could. Right now, the problem is the amount of energy it takes, the electricity it takes is more expensive than it's worth. But if we could do that, then we would have a great source of drinking water. In fact, it's this osmosis stuff is why it's not safe to drink salt water, seawater, because it will actually dehydrate you more, because now you have the stuff that's more concentrated on the outside of your cells, and so the fluid inside your cells are going to go from low concentration to high concentration, and essentially they're trying to water down what's on the outside, and in that process they're leaving your cells, they're dehydrating your cells, and so it causes a problem where you're dehydrating your body despite the fact that you're taking in fluids. But we could use reverse osmosis to purify that seawater. Like I said, though, the energy requirement, I didn't even realize that they talked about this down here, but the energy requirement is just too great right now. If we could come up with a renewable source of energy, like really good solar panels that we could then just pump that electricity straight into the reverse osmosis process, then it might become worth it. The other issue that you end up with is you end up with that stuff that was dissolved in here. When you start to push the water out of that, well, now the concentration of this goes up, and eventually if you get it too concentrated, then what happens is, just like when we're making a solution, we end up with a saturated solution, and then it starts to settle out of solution, or you can end up with a super saturated situation where it crashes out of solution, or if you've ever boiled a pot too long, you'll start start to get a ring on it. Heck, if you use a coffee pot too often and you look inside there, you'll start to get that lime scale in there is what it's called. You start to end up with stuff that was dissolved in the water, and that as the water boiled away, that stuff got left behind, and it's what makes the residue there. You'll sometimes see it as a soap scum ring in a bathtub or a sink. Well, that stuff starts to kick up, so we also have to have some kind of cleaning process that removes that stuff and then allows the new water to come in. So there are all sorts of engineering challenges we have to overcome, but it is a desperately needed solution that we would really like to engineer our way to, because it really could help with a literal global water crisis. So getting into some medical applications, here we're going to talk about different tonic solutions. Well, iso means same, and isotonic solutions have the same osmotic pressure outside as inside. And so you still have osmosis, stuff moving in, stuff moving out, but the rate of in versus out is the same. And so then you end up not affecting the blood, or more specifically the cells in the blood. And so this is important when giving IV fluids, that we have the fluids not just be pure water. There was a time where we did that and it caused problems because, again, we have this issue of having too much or too little stuff move one way or the other way. And we'll get into those examples here in a moment. But ISO means that it's the same, and so we don't have to worry about that. And based off of the normal blood glucose level or the number salt level in your body, then you'll have slightly sweet or slightly salty or slightly both IV bags that will be used to rehydrate someone so that it is not affecting the amount of fluid that's in there. From there, we have hypotonic. Well, hypo means low, and so we have a low concentration. We have a low concentration on the outside, a high concentration on the inside, and because of that, it will flow in more than it flows out, and that will actually cause the cells to swell up, and if we're not careful, it can cause them to then burst, at which point they become ineffective. On the other end, we can have hypertonic solution. Hyper means high, and so then here we have a high concentration out here and a low concentration in here, and so then the water flows out of the cells preferentially. Yes, you still have some going in, but it's less. We're talking about rates of moving back and forth, and so then it will cause them to shrink, and this process is called crenaceous. And there are times where we may want to shift it a little bit, but if we're not careful with the concentrations, then it starts to cause problems. Also, those numbers that were given on the isotonic solution there, the 5% and 0.9%, those are the normal for people. Sometimes you don't want to use NaCl and instead use some other alkali metal because of heart issues that some people have with high sodium, and sometimes it's absolutely necessary with certain illnesses to actually measure what the people have in there right now, so that you can match it. The other thing that comes up as well is some problems that a patient comes in with. Some disorders are going to be because they're already hypo or hypertonic, and so then we need to essentially address them with the opposite solution through an IV to restore the isotonic equilibrium state. My mother-in-law worked in a pharmacy in a hospital, and she said that was the thing she did most often, was dilution calculations and concentration calculations like we had in the prior section for making IV bags. She spent most of her day not dispensing medications, but adjusting IV concentrations and then having to label them. They, of course, had their standard ones that were just ready to go that were the normal ones, but she spent most of her time doing this. And at some point, she wanted a promotion that required her to get a certain licensure or degree, and she had been working there forever and knew how to do all this stuff, but then she had to study for this test, and she actually had me teaching her dimensional analysis, and I think maybe even I told that story back at the beginning of the course when I was teaching dimensional analysis, but she had me teaching it to her so that she could take that test and pass it just so she could go back to doing what she was already doing. And frequently, she had to prove that she could know how to do this for the rare situation where she did need to, but frequently she was looking at charts and tables, and they'd done these things often enough. They had just records of it, and they had diagrams that she could read, and okay, I need to mix these things in these proportions to create this thing that I've made so many times. And she said she had so many of those procedures memorized that she didn't even think about the table or the calculations. She just kind of knew how to do it. But a lot of times what we're doing here in college is we're going to give you a certain depth of knowledge. We require you to understand something to a certain point, so that when you forget some of it, you still remember the essentials. If we only go shallow and you forget some of it, then you've lost the essentials even. Sometimes it's just about proving that you can do something so that you can show that you're trainable and can be trained to do what you need to do on a job. Anyway, that's a little bit too long of an aside. But anyway, dialysis then is another case where we have this, where we can artificially allow things to pass through a permeable membrane and stop colloidal pieces. And this is naturally what your kidneys do. But if a patient's kidneys start to fail for whatever reason, we can put them through artificial dialysis that will take the place of the kidney and remove those waste particles that usually are colloidal in nature. Here we have a few practice questions. And for this, we're going to need to recall the 5% glucose and the 0.9% NaCl for these practice questions. But remember, if we're higher than that, we're hyper. We're lower than that, we're hypo. And if we're at that, we are iso. So 2% NaCl, that's too much, so that's going to be hypertonic. 1% glucose solution is going to be low, so that's going to be hypotonic. This one is also low, so hypotonic, and this one is equal to, so isotonic. So that would be number 1, 2, and 3, and 4 there if we label it the other direction. The last example here is similar, so I'm going to pull up those values again. That normal is about 5% for glucose, or 0.9% for NaCl, and that higher than that is hyper, and lower than that is hypo, whereas the normal is iso. Now, we're not asked to identify it as hyper or hypo specifically, but instead whether it will cause hemolysis or carnation. Well, the way that I remember this is the hemolysis is related to the hypo, that they both have that O in the middle, and so this one's going to give us the hemolysis, which means this one here, the hyper, must give us the crenation. So 5% glucose, that's what we expect, so that's going to be no change. 1% glucose is low. If we're low, we're hypo, so that's the hemolysis, which is B. Then we have 0.5% NaCl, that's also low, so that's also hemolysis, and 2% NaCl, that is high, and so that's going to be hyper, which gives us crenation. As I mentioned back at the beginning, I wanted to address a couple other properties that your textbook doesn't address. You're not going to be tested over them, and they're not going to come up in homework problems. If you're with me live, I may do a demonstration, or we may even do a lab over one of these other properties. But one of them is something called colligative properties. And interestingly, colligative properties do not depend on the substance involved, but rather just the amount. Osmotic pressure, that we talked about, is actually a colligative property. It doesn't depend on what substance it is, it just depends on the concentration, the amount of stuff that's there. There's another one called boiling point elevation and freezing point depression. You've probably heard before that adding salt to a pot of water will make it boil faster. That is not true. It might make it boil hotter because it actually raises the boiling point. And so if your stove is pumping out a certain amount of heat, it's going to take longer to get to that higher temperature. If it just keeps pumping out heat at a constant rate, if the water has the salt in it, the salt will elevate the boiling point. It'll make the temperature go up, and if the stove is producing that constant rate of heat, it's going to take longer to get to that higher temperature. However, it will then be hotter and could cook things faster. Now, I say all of that with the caveat of you have to add a lot of salt to the point where your food will be unpalatable. Usually when you're adding salt at the beginning, it does nothing significant to the boiling point. Like it's going to take it up less than 0.1 degrees Celsius. What it will do, though, is it'll flavor your food nice and yummy. Having said that, this is also why, with the freezing point depression, how we can use salt on the roads to get snow and ice to melt in the winter. Tossing down that salt in the road, it turns out you have some liquid water there, that it's not all solid water, and then that little bits of liquid water that's there, the salt will start to dissolve in. Well, now we have a salt water solution, and salt water just naturally has a lower freezing point than what regular tap water does. Well, it turns out it doesn't matter whether it's sodium chloride salt or calcium chloride salt, really. It depends on how much you put in there and not actually what you put in there. It really comes down to how many pieces does it break down into. So the NaCl breaks down into 2 pieces, and because of that, it has the effect of anything else that has 2 pieces. If we had that be potassium iodide, it'd be way too expensive to toss on roadways and sidewalks, but it would have the exact same effect because it's the same number of pieces that they break down into. Calcium chloride, though, which are sometimes sold as pellets, if you buy the brand of salt that has the Roadrunner on it, that's the calcium chloride salt. It breaks down into 3 pieces. It'll depress the freezing point even more. It'll lower it even more, and so it works better. The problem is it's more expensive. And conversely, it would have the same effect on boiling point. The way that I remember those two is just that they go apart from one another. Boiling points go up and freezing points go down. The range gets bigger, and that just has to do with the natural properties of a saltwater solution. If you just make salt water and then try to freeze it, it has to be colder to get it to freeze. But how many pieces it breaks down into is something called the Van't Hoff factor, and is abbreviated with a lowercase I for some reason. Anyway, that's one. The other one I wanted to mention is the Beer-Lambert law, sometimes just called Beer's law, which says that A is equal to A times B times C. This is absorbance. And then we have concentration. This one here is path length. And this one here is the molar absorptivity. And really what this is that we can measure how much light is absorbed by a solution, then it will have a fainter color. Now, I'm limited as to what color palettes I have to work with here in the software, but I think you get the idea there, and you've, of course, have seen things like this before. But what is interesting here is if we shine red light through these, the red light is just going to go right through the solution. And that has to do with just the properties of light. The reason that my shirt appears blue is white light shines on it. It absorbs all the colors except for blue, and it reflects blue. Of course, there's different shades of blue, and that's because it doesn't just reflect blue. It reflects a mixture of a range of blues and maybe some hints of some other colors in there. Well, the same thing's true for clear things. Think of a greenish bottle, say a Mountain Dew bottle. It not only reflects green light, but it'll also transmit. That is, it lets it go through. However, there are opposite colors on the color wheel if you've taken any art classes and gone into the color theory kind of things there. Well, it turns out that green is the opposite of red. Well, if we shine green light through here, not as much of it gets through. I can't make the green here be faint, but what happens is that really the light comes in and it kind of gets stopped and less of it makes it through. Well, when there's it's more watered down, then there's less particles in there to absorb it, and so then not as much gets stopped. I drew it here as it gets stopped further along the path there, but not as much gets stopped, and so then it lets through more light. Well, we can measure how much light gets through, and that is called transmittance. And we can turn transmittance into absorbance, or we can just flat out measure absorbance. Instead of measuring how much gets through, we're really measuring how much didn't make it through. And then we can measure this one in the lab for any colored solution. We can also do it for some clear solutions if they absorb infrared or black light, that is ultraviolet light, but it's easier to just think about it in terms of colored solutions. We can measure how much it absorbs. Well, it turns out that every chemical has its own molar absorptivity, that at a certain concentration, it will absorb a certain amount of light. Well, then from there, what matters is how much liquid did we put it through. So we actually have to pay attention to how long that liquid is. And if we're really picky, we have to factor in the container itself, because the container itself, the glass container, could absorb some of the light, does absorb some of the light, does reflect some of the light, and so we have to factor that out. But then we can measure the path length, and we know how much liquid is there, and between knowing those three values, then we can calculate the concentration. There's also another way that you can do this. You could do something called a serial dilution. And with a serial dilution, you start out with a dark color in here, and then you pour, let's say, half of it out into a new container, and then you water it down to where it's the same volume, and you keep repeating that. Well, it gets fainter and fainter and fainter and fainter each time, but it's not a linear relationship. It's a curved relationship. It's not a straight line. It gets significantly fainter, and then you can do the Beers-Lambert law to check your dilutions there. It's also sometimes necessary if the original solution was too dark to let any light through. If just all of it gets absorbed, it goes in and it just flat out stops and it doesn't actually make it through. You sometimes have to water it down maybe a few times, keep track of how much you watered it down, and then you can measure the concentration of this, and then from measuring the concentration of this, you can work your way backwards to how concentrated it was originally. Again, for those of you who are with me live, we'll at least do a demonstration of this, if not a lab activity over this as well. The last thing I'll point out is something I failed to mention with the colligative properties, and that is colligative properties, because they don't depend on the substance, but instead just the amount of the substance. They are measured using one of those other concentration units that I mentioned way back when we were covering concentration, and that is something called molality, the one that's abbreviated with the lowercase m, and it wasn't covered in our formulas because it's not a solute over solution, it's a solute over solvent, and so the calculation is just a little bit different, and we were trying to stick with the different ways to do the same kind of calculation, solute to solution, in this topic. There are, of course, other properties, but we're going to just leave it off at those key ones. As usual, there's a concept map here at the end. This one's okay, so pause it, take a look at it. But that not only finishes up this section, but also this chapter, so be sure to let me know if you have any questions.